Probably we're one of the unique talks here. We're talking about like healthcare use case of ML. But yeah, first of all, thanks Deval for the introduction. Takes one part out of the talk. And yeah, also thanks to the organizers and for giving us this nice chance to talk about something that we've been working on for the last 5-6 months. So what we're doing, Valli, I and our colleagues at Vector, we're trying to develop a framework for building data pipelines and model evaluation, but targeted to like clinical use cases. And we're approaching this in a more unified way because currently they're very fragmented and they're like kind of decoupled. So in our talk today, we have like two main themes. In the first half, I'll be talking about health data, specifically EHR data, so electronic health record data, and the issue of standardization, which is currently one of the biggest challenges towards doing effective machine learning in the health space. And in the second half, Valli will be talking about model evaluation and monitoring ML models towards deployment in actual hospital setting. So so a while back, our team started working with this large retrospective EHR data called Gemini. And this data set was basically data collected from 7 different hospitals in the GTA region. And so essentially EHR data is when you go for, go to the hospital, it's any contact that you have with the healthcare system is recorded. So if you go into the emergency room with an injury or some complication, what does the physician do, their initial assessment, all the timestamps, all the lab tests that are ordered, vital measurements, everything is sort of recorded. And EHR systems have been around for about like 10, 15 years now. But in the last 5-6 years, a lot of interdisciplinary people, including like machine learning scientists, started looking at this data and thought, okay, what can we get out of this? What can we do that can like help doctors and free up their time? Because a lot of doctors' time today is spent on entering data, recording it, analyzing different sources of data, when they should be actually talking to patients and improving, their decision making for like diagnosis, and also like having a more one-to-one conversation with the patient has become very, sort of limited now, like compared to like several years back. Now it's like you hardly get time with the doctor to really explain and what's going on. So we want to help with that, and so we started looking at it, and some of the things that we kind of identified early on was this data is very non-uniform. It varies across hospitals, across time. Different hospitals use different EHR systems. So like one hospital could be specializing in cardiovascular diseases. Another hospital will have a different process of acquiring and recording data. So it was very messy and very unstructured, and there was no sort of shared data model. So coming to that, common data models are at the very early stage in the health space, like towards actual adoption. And so we saw that like there were a lot of machine learning people starting to work with this data, and they had to do a lot of curation steps to actually get to be able to identify the right set of features and the right representations to actually like know what kind of use cases they can use it for. And even more confounding is like in the health space, like the ground truth is like very hard to even like know, because doctors' diagnosis, or if it's like a certain complication, it's a very qualitative judgment. It goes through several reviews, so the quality of that is hard to obtain. It's a very painstaking process. So all of this is very heavily tied to the problem of like being able to use machine learning on top of health data. And finally, researchers really need a high degree of flexibility to be able to transform this data towards actual like representation. So one researcher might want to model it like using time series, and so like LSTMs, RNNs. Someone else might want to like tokenize it and treat it more like similar to like language model representation. So there can be all sorts of things in the way they try to transform this data. So I sort of started thinking about it, and I think it can be broadly categorized into three levels of standardization. So at the lowest level, you have like variable names and data types, right? This simple things, right? Like when you go from one hospital to another, when you say, I took this test, people should be able to understand the same terminologies. Same thing with like, I used this unit of measurement, or I used a variable, a string data type to represent this information. So it should be sort of consistent across sites. The second level is when you start aggregating this data into different tables and start having relationships between these tables. That should be sort of uniform as well. Like for example, you can have a table where you have information on blood transfusions that was done, or dialysis, or interventions that was done during a patient journey. So, how do you map all those concepts to, in a way that is consistent across different locations and hospitals, so that people can work on like the same data format. And finally, how do you exchange this data? Like, what kind of web standards can you use, like XML, JSON? What kind of like RESTful API design do you want to use to actually share this data? So all of these need to be solved. So a while back, the Observational Health Data Sciences and Informatics Committee, they came up with a book, essentially, which talked about their suggestion for a common data model, and it's called OMOP. And that essentially solves those three levels of standardization issues. So you can go from multiple sources, transform it to OMOP, and then now suddenly you can build common APIs for analysis and possibly machine learning things downstream. So how does that actually look like? So you have standardized vocabularies. So you have like a very generic concept names where different information can be mapped into. You have, so whenever you look at EHR data, again, EHR is only a small subset of all kinds of health data. There's like imaging, genomics data. So this is specific to EHR, but the idea is like you want to aggregate like, say, patient level data or encounter level data, and that goes into different fields and maps into different concepts. And so you have standardization of the overall schema and how you store metadata and stuff. So they came up with this, and people started using it, and it's very early still. Like, not a lot of hospitals are using it, but a lot of people are paying attention to it, and we really like this concept, and we think that we want to really integrate it. And so we started, there are a bunch of data scientists who started mapping the Gemini dataset to the common OMOP format. And so we're going to be using it very soon. And having that, so understanding those issues, we set out to actually build the framework. And so our design kind of looks like this. I don't know if the font is probably too small, but I'm going to go over it. So typically you start on the left, you have like data coming in from hospitals. They are like stored to create these retrospective data sets. And so the first thing that we decided that we need is some API to be able to like query this data, right? So these are relational databases, so everyone knows about SQL. But the thing is that machine learning researchers don't like SQL. They don't like to use SQL to like, it's hard to maintain. It's also like, it's just a pain in the ass if you have to like actually like, scale it towards multiple use cases, be able to parameterize things. So one of the things we realized was, okay, let's create something very close to Python. So we used SQL Alchemy to build an API to be able to very easily pull out data from different tables, join them, filter on different attributes. And so that essentially became like the first stage of the pipeline. The second part is a processing API. So this is what I was talking about before, where researchers want a lot of flexibility. So when you go from like the initial raw tabular data, you want to do things like aggregation. So for example, let's consider a window of like, say, 24 hours since the patient was admitted, and let's bucket it into 6-hour time steps and aggregate different information. So being able to do that, being able to deal with missingness, which is a big problem in health data, because like patient comes in, a certain test or some measurement is done, and then for the next 5 hours nothing happens, and then they do something else, and then for another day nothing happens. So it's very non-uniform. So being able to handle that in a very flexible and modular way is what we want to do with the processing. And whatever processed features and representations come out of the processing API is added to a feature store. And for the feature store, we are currently using Feast. And the processing, most of the processing functions is on Pandas. I mean, Pandas is like the default library for processing like tabular data. It's very mature library. It's got like very highly optimized functions, so we're using that. And so after you add these features to the feature store, that's where the interface is with all the downstream tasks like model training, evaluation, dataset shift detection, and visualization. And for orchestrating like the data pipeline workflows, currently we're using Luigi, but probably this is like flexible. We can easily switch to Prefect or some other tool as well. And then finally, so this is all in like a research setting. So it's to do with the retrospective data. So now you've trained a model, you've seen that, you've evaluated it, it looks good, you want to go and try it out in a hospital. So for deployment, again, the standardization is an issue. So there is another open exchange format called FHIR, which is becoming a widely adopted standard. So we haven't yet implemented this, but this is in our roadmap that for the later part of this year, that we will basically add an interface which will map all the variables coming in from raw hospital EHR systems, and then map it to FHIR format, and then which our processing API can then understand. So how does the querying look like? As I said, we wanted it to be very easy to use, similar to like how people like to use simple Python functions. So for example, on the left, if you want to get patient encounters, filter on some years, months, specific date ranges, you can do that. If you want to get event data, you can do that and filter on like things like what kind of vital measurements do you want. You can filter on specific ones like heart rate or temperature or glucose measurement and all sorts of things. And currently we have done this for 2 data sets. So one is the one that I mentioned, Gemini, which is the one that we really want to develop applications and things on top for our healthcare partners. But the other is a publicly and available data set which researchers really have done a lot of work on, which is Mimic. And in the future, we see the framework extending to multiple data sets, just because we think that if you choose one data set, you will start optimizing towards one type of like data set and how it looks like. But we really want to identify the general patterns across data sets and build something that's more generic and like generalizable to multiple use cases. So that's why we started off with 2, but eventually we want to add more and more modalities as well. So yeah, this is how it typically looks like right now. You have a bunch of these tables, and you have the querying API. It pulls data from multiple tables, does a bunch of filtering, joins, and then it spits out pandas data frames. So the processing API, the high-level sort of pseudocode can be something like this, and this is how it looks like today. where let's say there's like 2 steps that you want to do in the pipeline, which is, say the first is aggregation. So you consider like a window, a step size, which is like 2 hours or 3 hours, depending on how frequent measurements are made. And this is, again, needs to be very flexible because like if you go to the ICU, measurements are made way more often. If you're in the general internal medicine ward, it's much more sparse. So being able to handle those kind of different use cases. And then now let's say you want to impute missing features. So you want to like, and there are like there's a lot of research like on how to treat missingness. And so we initially said, okay, let's build a generic sort of abstraction for imputation, and then people can plug in whatever imputation techniques they want to use, right? And finally, the way it's done is just run it as a pipeline, so you can like you can do aggregation first, you can like followed by imputation or other steps in between, and you can treat it as essentially like a directed acyclic graph. So yeah, that's so far with the data processing side. I'm going to pass it over to Valli to talk about evaluation.
Yeah, so thanks, Amrit, for the great bit about the data. So clinical data, it varies so much compared to other domains, but that also holds true for evaluation and monitoring. So yeah, the clinic differs from a lot of other domains because it's a very high risk setting for model failure. So say you have a machine learning model, you're predicting some sort of outcome, and that outcome is being factored into the decision-making process for a clinician, whether that be like diagnostics, treatment, whether that means changing the surveillance protocol. Ultimately, it has an impact on the patient's survival outcome. So as a result, it's really important to make sure that these models are not biased. There's several sensitive attributes in clinical data that have to be monitored for things like dataset shift. So ethnicity is a big one, gender, marital status, age, insurance type are just a couple of them. So prior to deployment, it's really important that these models are obviously evaluated very robustly, but then during, or once the model is deployed, it's really important that they're also frequently monitored for signs of model deterioration. So if we know a priori that a model is going to deteriorate, then a clinician can maybe know that and factor that into their decision of whether they want to include the model's decision or if they want to override it per se. And that can also be used to develop strategies to improve the model as well. And so all of these should be done with principles of model explainability and trustworthiness in mind. So yeah, evaluation differs a lot in the clinic. And so although standard metrics are really valuable, they offer only really shallow insights. And so it's really important to take the actual clinical scenario into context. And that's kind of where clinical MLOps differs from other contexts. So in a lot of these models and how they're built, as Amrit was saying, they're usually built on retrospective data. And so retrospective data is great in some ways, but also has a lot of issues. So if we take sepsis as an example, and you're building a model to predict whether or not someone is going to undergo sepsis in the next 4 hours, the retrospective data, you're deriving the labels, the outcomes using the retrospective data, typically billing codes. And billing codes are great because they have a high positive predictive value. You're likely predicting patients correctly, but then at the same time, when you compare them to clinician reviews, they have a much lower sensitivity. So when you are building a machine learning model and you're building on labels that are inherently less sensitive, your model is obviously going to be biased. So it's really important to consider this kind of risk versus benefit trade-off. How many false warnings do you want in the ICU versus how many patients do you want to miss? And even for benchmarking, it's really important that the models are compared to clinicians and the clinical scenario in a really accurate way. So a lot of these models, for example, if we take a model that takes pictures of skin abnormalities and predicts whether or not someone has a malignant or benign skin lesion, a lot of them, when they do the actual testing, they essentially give the clinician a bunch of photos, and then the clinician has to say whether or not this is malignant or benign. But in reality, that's not really an accurate test to compare a model to, because the clinician has so many more resources available. They have their colleagues who they can talk to. They have past cases that they can refer to. So it's really important to evaluate these models in the true context that it would be deployed. And so if, for example, this model is deployed and the clinician gets a prediction of sepsis and they decide, or that the patient's not going to undergo sepsis, and they decide, I want to override the decision that the model has made. And so if they decide to do that, it's really important that that information is factored into the model evaluation so that the model can be improved in future iterations. So on that note, it's really important to choose the right metrics for evaluation that kind of cover different principles of generalization, calibration, and that's just say confidence. I think the slides got a little bit messed up with the transfer. So generalization obviously is very important because I think a lot of the times in the clinic people think false negatives are what you want to minimize. So that's patients that you're missing. But in a lot of contexts, false positives are also really important, and it's important to choose metrics that reflect both. So an example is in the ICU. You obviously don't want to miss a patient, but in the ICU, time is of the essence. And so if you are having a lot of false warnings, that's time that can be spent with the patient that actually needs the care. So generalization is a really important principle to keep in mind when choosing metrics. Calibration, of course, to ensure that the model is calibrated as close to the training data set as possible. And things like confidence. So you want to know a clinician, when they are making a decision for whether or not they are going to factor that model's outcome into consideration. They want to know how confident the model is. And for things like if you're predicting dosing for a drug, you want to have a prediction interval, right? So you want to know if you're going to administer a certain dose, how much should you modify that? What's the kind of window that's appropriate to do so? And so in the clinic, dataset shift can occur in a variety of different ways. Because of this, it makes it really complicated to monitor it. It's a very multifactorial problem. A lot of these can occur concurrently. And so one really big one is technology. So here in Canada, a lot of hospitals use the Epic system to store their EHR data. But there's also a lot of hospitals that don't use the Epic system. So Mount Sinai uses Cerner. Sunnybrook uses their own in-house system. And so each hospital is documenting their EHR data in a really different way. And so that means different labels, different features. And so that's why things like the data processing really play a role into unifying that. But then even beyond that, there's things like the behaviors and policies in place. So whether or not a certain test is done for a given diagnosis, that differs between different hospitals. And then things like demographics. So between each hospitals, that there's different kind of populations of people, and that say certain ethnicities have a higher rate of certain diseases. And so things like that can all cause data set shift. And in the clinical scenario and in tabular data and EHR data, this isn't as established. It's not really well known what metrics are well known or good to use in this setting. It's not really well known what methods work well. In imaging data, this has been a lot more established and benchmarked. So on that note, it's really important to know this type of information before a prediction is made. So model performance is obviously very important and is a really great sign of model deterioration, but in the clinical setting, labels are very costly. And so an example is if you have a model that is using chest x-rays to predict pneumonia and things like that, a radiologist has to come and actually provide a label for each of these. For some use cases, the lead time is really long, so you won't have a true label for months, sometimes years. So it's really important to be able to do dataset shift in a label agnostic way. And so this is the strategy that we're taking, essentially inspired by this Failing Loudly paper, as well as some other methods and other papers. And so essentially, you have a source data and a target data. We're doing some sort of dimensionality reduction, and then doing a two-sample multivariate test. And then you can get an actual p-value, which you can use as your detection threshold. So this is an example of one of these data set shift experiments in our data that we're using from Gemini. So as Amrit mentioned, Gemini is a really great resource right now for us. It's a really good use case because it has over 600,000 patients from over 30 plus hospitals in Canada, and it's growing. It's all patients from the general internal medicine ward. And so essentially for this experiment, what we did was we had pre-COVID data and COVID data. We first, our pre-COVID data was our source data, and our COVID data was our target data. And you can see that when we actually look at the number, as we increase the number of samples along the x-axis, the p-value actually decreases for the COVID data. So you see a data set shift in the COVID data, but in the pre-COVID data, which is our baseline, you're not seeing that shift. And then that shift is actually also reflected in the model deterioration. So you can see that the AUC for the actual COVID data is much lower than that of the pre-COVID data. And so having this type of information before a model is actually predicting is really valuable. And that's also not all you want to know. You want to know why the model is shifting, what's changing, and so explainability is really important. So here I'm showing the SHAP values, which is a way to assign feature importance by breaking down a prediction based on what feature is contributing most to that prediction on an individual person's basis. And so here you can see the SHAP values, the mean SHAP values between COVID and pre-COVID data in our model. And you can see that the variables that change the most are the ones that you would actually expect to be associated with COVID. Things like heart rate, respiratory rate, high sensitivity to troponin, which is associated with like cardiac arrest. So things that are known now in literature to be associated with data set shift. And so this is really valuable because knowing that a model is shifting is one thing, but knowing why it's shifting is obviously much more valuable from a clinician's point of view, and it builds trust with the clinician as well. So with these AI models, really becoming more and more popular in clinical use cases, it's important to establish guidelines for evaluation and monitoring. And so these are slowly starting to be established, similar to how you have clinical trials for drugs. And so we hope that our work and similar work like this will help build these types of guidelines. So things like how frequent you would need to monitor a data set shift, and the types of data set shift you want to look at. Things like that through our experiments and our eventual pipeline, we hope will enable people, other researchers, other individuals who are deploying clinical models to do that. So overall, our key takeaways from our presentation, we see that health data is very unstructured, very messy, and as a result, there is a need for a unified and easy-to-use API. That common data models like OMOP and FHIR are at very early stages of adoption, but once they do become a part of the picture, will make a huge difference in unifying the data. And that evaluation is really context-specific in clinical cases, which is different than other domains, and it requires really constant two-way feedback between clinicians and machine learning experts for improving models in future iterations. And so a unified framework for MLOps in clinical data sets is obviously very important, and it's important to automate the data processing pipeline for reproducibility, evaluation, and other barriers to deployment. And ultimately, it would accelerate research initiatives because there's a lot of models in the research setting which they perform well in a retrospective way on retrospective data, but they haven't actually been deployed in the clinic because there's no established way or there's no frameworks to actually support their deployment. So our future directions, we want to support querying for the OMOP format data sets, and that would encourage other hospitals to join and other members of the community to adopt these common data models, add conversion to EHR data to FHIR resources, and update our processing API to handle them for deployment. And then also for our data set shift and monitoring, we want to adopt more use cases. So we have a partnership right now with Trillium Health Partners for a clinical imaging data set use case. And so the idea would be there's a model to predict outcomes with chest x-rays, and we'd like to kind of monitor in real time, are we able to detect model degradation, data set shift, and all these other important metrics. And yeah, that's all we have. Thank you so much for listening. We are also hiring, so if you're interested, love to work with you guys. And yeah, do you have any questions for us?